vLLM, the key to running AI models on local networks. Summary. vLLM is an open-source inference engine designed for fast local AI deployment. Using its key innovation, PagedAttention, vLLM manages GPU memory efficiently to eliminate waste and dramatically increase user capacity. With features like continuous batching, quantization, and multi-LoRA serving, it delivers top-tier throughput. Its built-in OpenAI-compatible API server makes local network integration seamless, allowing organizations to securely host high-performance language models inside private network environments. 1. Introduction: the local AI bottleneck. In recent years, large language models, LLMs, have transformed how businesses, researchers, and developers work. From writing software code to summarizing complex documents, AI tools are now essential. While cloud-based services like OpenAI's ChatGPT or Anthropic's Claude are widely used, many organizations prefer running AI models locally on their own hardware. Hosting an AI model on a local network provides complete control over data privacy, removes monthly subscription fees, and guarantees that sensitive information never leaves the organization's firewall. However, serving LLMs on local hardware presents a significant technical challenge. Traditional machine learning frameworks were built primarily for training models, not for serving fast text generation to dozens of simultaneous users across a network. When multiple users send prompts at the same time, traditional setups quickly run out of graphics processing unit, GPU, video memory, VRAM, or experience dramatic slowdowns. This severe performance bottleneck led to the creation of vLLM, an open-source, high-throughput LLM inference and serving engine originally developed by researchers at UC Berkeley. By redesigning how GPU memory is handled during text generation, vLLM allows local servers to process network requests significantly faster and handle far more simultaneous users than traditional setups. 2. Memory management and PagedAttention. To understand why vLLM is a game changer for local network deployment, it helps to understand how language models generate text and use memory. As an LLM generates a response token by token, words or parts of words, it calculates intermediate attention vectors. To avoid recalculating these vectors for every single new word, the system stores them in GPU memory in a temporary store called the key value, KV cache. In standard deep learning engines, memory for this KV cache must be allocated in advance as one continuous, unbroken block of VRAM. Because the engine cannot predict how long a user's prompt or final response will be, it conservatively reserves enough contiguous memory for the maximum possible context length, for example, 4,000, 24, or 8,192 tokens. This traditional approach leads to massive memory waste. Fragmentation. Memory gets broken into tiny, unusable gaps, similar to an over-cluttered hard drive. Over-reservation, up to 60% to 80% of GPU memory ends up sitting empty, reserved for tokens that the user never actually generated. As a result, a powerful GPU that cost thousands of dollars might run out of memory after handling only 2 or 3 active users at once. vLLM overcomes this hurdle through a core innovation called PagedAttention. PagedAttention borrows concepts from virtual memory management in traditional operating systems. Instead of forcing the KV cache to occupy one large continuous chunk of memory, PagedAttention breaks the cache into small, fixed-size blocks, pages. These memory blocks can be stored anywhere in physical GPU VRAM. A central lookup table maps virtual sequence positions to physical memory blocks on the GPU. Because memory is allocated dynamically on demand in small chunks, wasted space drops to near 0%. This memory efficiency enables vLLM to fit much larger batch sizes into the same GPU, boosting overall request throughput by 2 to 4 times compared to standard frameworks. 3. Key architectural features of vLLM. Beyond PagedAttention, vLLM includes several production-ready features that make it a leading choice for AI serving engines. Continuous batching. Traditional serving engines process network requests in static groups. If 3 users send prompts simultaneously, the engine groups them into a batch and waits until the last user's response is fully completed before starting any new requests. If user A asks for a 1,000-word report while user B asks for a 1-word answer, the GPU sits partially idle waiting for user A to finish. vLLM implements continuous batching, also called iteration-level batching. The engine dynamically adds new incoming network requests into the GPU execution queue token by token. As soon as one request completes, its memory is freed, and a waiting request fills the slot instantly on the very next token iteration. This ensures the GPU operates at near 100% capacity at all times. Advanced quantization support. Large AI models require huge amounts of memory. For example, running a 70 billion parameter model in full precision requires over 140 gigabytes of VRAM just to hold the model weights. vLLM natively supports modern quantization formats, including FP8, AWQ, GPTQ, bits and bytes, and GGUF. Quantization compresses model weights into smaller 4-bit or 8-bit number representations with virtually no loss in response quality. This enables organizations to host powerful, state-of-the-art models on affordable single workstation GPUs. Multi-LoRA serving. In an enterprise network, different teams often need specialized AI capabilities. The marketing team might need a model trained on brand copy, while the engineering team needs a model tuned for software debugging. Loading multiple separate 70 billion parameter models into GPU memory is impossible on a single machine. vLLM solves this with Multi-LoRA, low-rank adaptation support. A single base model stays loaded in VRAM, while lightweight adapter modules, LoRAs, are swapped dynamically per network request. One vLLM instance can serve dozens of custom fine-tuned models simultaneously without duplicating base model memory. Automatic prefix caching and speculative decoding. In many business applications, user prompts share long, identical text fragments, such as system prompts, company guidelines, or uploaded document chunks. vLLM's automatic prefix caching automatically detects shared text prefixes and reuses their KV cache blocks across different user requests, eliminating repeated computations. Additionally, vLLM supports speculative decoding, where a tiny, ultra-fast draft model quickly generates candidate tokens, and the primary large model verifies them in parallel. This accelerates generation speed without sacrificing accuracy. 4. Deploying local AI across networks with vLLM. While raw performance is critical, an inference engine must also integrate easily into real-world computer networks. vLLM is specifically built to simplify local network deployment. OpenAI-compatible REST API server. vLLM includes an out-of-the-box API server that implements the standard OpenAI REST API format, such as the /v1/chat/completions endpoint. Because OpenAI's API design is the universally accepted standard in AI software development, virtually any open-source user interface, such as OpenWebUI or LobeChat, or developer framework, such as LangChain, LlamaIndex, or DiFi, can connect directly to a local vLLM server. System administrators simply point their local software's API URL to the vLLM server's local IP address. Distributed multi-GPU and multi-node scaling. When an AI model is too large to fit on a single GPU card, vLLM uses tensor parallelism and pipeline parallelism to split the model across multiple GPUs inside the server. If the model exceeds the capacity of a single server chassis, vLLM integrates directly with Ray, a distributed computing framework. This allows network administrators to cluster multiple physical server machines across a local area network, LAN, pooling their hardware into a single unified AI endpoint. Privacy, control, and infrastructure integration. Deploying vLLM locally guarantees strict data governance. Because all prompts and responses travel exclusively over the local network, proprietary data, medical records, or legal contracts remain completely safe from third-party cloud monitoring. Administrators can easily bundle vLLM into Docker containers, orchestrate deployments using Kubernetes, or manage user access using reverse proxies like Nginx for rate limiting, load balancing, and encrypted SSL connectivity. You can save money and improve security by running local AI models on your PC or Mac. Applications and models are available for free. I can help you get up and running. Contact me for a free demo. You need a PC or Mac with 16 gigabytes or more of memory. I have published more than 700 blogs on AI in the past 3 years. If you get value from these blogs, please join my Patreon as a member at the $2, $4, or $8 per month level. https://www.patreon.com/Steve Hovland. I have a new group on Facebook called GPT-4ALL by Steve Hovland. GPT-4 All is a free program that lets you run AI models on almost any PC or Mac. It lets you keep your private data private